committee, for the organizer for inviting me. So today I'm going to present our recent results on the development of porous nanostructure, of course in our laboratory. So porous nanostructure aluminosilicates, it can be synthesized in your laboratory, or it can be naturally occurring. So as you can see, there are many structures of the synthetic aluminosilicate, but most of them are zeolites. So now there are over 200 type of structure of zeolites which you can find in International Zeolite Association database. So so many of them, but there are the most famous is MFI, which is ZSM5. You all may have been familiar with ZSM5 or fungicide or chabazide, as well as the, this is not zeolite, but this is mesoporous material, MCM41, ordered mesoporous material. And it can also, the zeolite can also be present in nature. In Indonesia, we have several sites of natural zeolites, but most of them are clinoptilolite or modernite. And it can be also amorphous, which is silica, which you can find, for example, in rice husk. Rice husk consists of at least 15 to 20% weight of silica. So, zeolite. So this is zeolite. In macroscopic, you see it is as a white powder. But if if we zoom to the structure, this is the crystal of zeolite. And if you go further, you can see this is the electron microscopy, the TEM image of zeolite ZSM5. And zeolite, most of zeolite, all of the zeolite are microporous, which has the pores less than 2 nanometers. Okay, it is arranged by tetrahedral units. TO4, which is T is silicon or aluminum. It has large surface area. In 1 gram of ZSM5, it has pore length of 6 times 10 to the power of 11 meter. So it is 4 times the distance from Earth to Sun. So that makes it is one of many reasons why zeolite are good as catalysts. And also it is acid. Why? You see, there is silicon, and the silicon is substituted by aluminum, and it has negative charge. So the negative charge can be balanced by proton. So it gives the zeolite an acidity. So this is ZSM5, but ZSM5 has been found by the mobile scientists. But in fact, the structure has been predicted long way ago. This is a pattern on the wall in Omas in Azerbaijan 1,000 years ago, and this pattern is the exact same as the structure of zeolite. So there is nothing new under the sun. But zeolite is the main catalyst, applied in the petroleum industry. But in fact, it still has serious issues, which is the diffusion issue. Okay, which is the diffusion issue. Why? Because zeolite is microporous. The pore is small, relatively small, less than 2 nanometers. So either the molecule cannot enter its active site within the pores, or the products which is resulted in the active site cannot go out from the micropores. So it results in coats, which deactivate the zeolite, so that zeolite cannot be active as catalyst. So what is the solution then? the solution is one of several solutions is by introducing the mesoporosity. So mesopore is larger pore. It's a larger pore, larger than micropores. So it's from 2 to 50 nanometers. So it's larger than our micropores. So it gives better mass transport because now the diffusion path is larger. It's like you drive a car in fall in highway versus you drive a car in Margonda. It's different, right? So this is one of the facile solution to overcome the diffusion issue within the purely microporous zeolite. So here's some of our results regarding this. We published this 3 years ago in microporous mesoporous material. So we synthesize the zeolite not in autoclave, but we lower the temperature below 100 degrees C. So we can conduct the experiment just in a polypropylene bottle, not in the autoclave. Okay. So if we reduce the temperature, so the rate of crystallization will also decrease. But to overcome this, we lower the amount of water so that the concentration will increase, and it will compensate the rate deceleration caused by the decrease of temperature. So as you can see, if we lower the temperature, there will be formation of numerous nuclei. So it means numerous nuclei, it will result in small crystallites. So these small crystallites will aggregate to form aggregation. It's aggregation of small particles, which gives mesopores. So we can synthesize mesoporous zeolite without the addition of additional organics, because it is often, if we want to synthesize mesoporous zeolite, we add some organics like surfactants or something like that. But now we can synthesize the mesoporous zeolite, or sometimes we call it hierarchical zeolite, without the addition of additional organics. And you see, it is different. It is different with the conventional ZSM5, which has hexagonal prismatic morphology, or sometimes it is called coffin type, because it's like the coffin. This is purely microporous. You can see it is highly crystalline. You can see also the nitrogen absorption, desorption isotope. It has the H4 hysteresis, which indicate the occurrence of mesopores. And so this is the bottom-up strategy. We also have another strategy, which is the top-down. Use the desilication. So if you have microporous zeolite, you can treat using alkaline solution, and it will leach the silicon, resulting in the mesopores. This is good for ZSM5. But how about this one? This is AZ13. It has the framework of chabazite. It is very powerful catalyst for the methanol to olefin reaction. Okay, a colleague has tried to use this strategy to apply to the LZ13, but it doesn't work. It doesn't work because the alkaline solution, decrease or induce the amorphization, so that your crystalline material will become amorph. So this conventional or this common technique cannot be applied to LZ13. So what do we do? When we synthesize the LZ13, we use this OSDA, trimethyl adamantyl ammonium hydroxide. We use these organics. So when we have synthesized this, we make variation, using the calcination. So AS means synthesized, it has 4 organics. C250, it means we calcine at 250 degrees so that the organics will decrease, will degrade and decrease, the amount will decrease. When we make variation to the organics content, what do we find? See, the temperature removal, it is seen as a function of the temperature calcination. This is the AS, full organics. When we calcine 250, the amount of organics is decreased. And when we calcine with 550, there's no organic. There's no organic. See, there's no organic. So you'll see when we apply the alkaline treatment. See, these 2 samples still highly crystalline. Still highly crystalline. This is the without alkaline treatment. This is after the alkaline treatment. So the crystallinity is maintained, is preserved. But for these 2, amorph, because this is no organics. This is very less organics. It cannot protect the hydroxyl attack to the siloxane bonds. And it is confirmed by the Raman spectroscopy. You see, this is the peak of the band for these 6R double 6 rings, still maintaining the structure of SZ30, but these 2, it confirms the result of XRD. And you'll see this is the SAM and TEM. When you have the SZ13, the purely microporous SZ13, you see the cubic crystal with smooth surface. When you apply the alkaline treatment, when you still have organics, you see the surface getting rougher, showing the formation of mesopores. And you'll see the electron diffraction still crystalline. But going to the last 2 samples, it is destructive. The crystal are destructive. And you see the electron diffraction, no better, amorphous. And we try to apply this, because we don't have facility to test the methanol to alphanes reaction, but we test on the LDPE, which is plastic, plastic catalytic cracking test. So you see, we use this Arrhenius-like plot, it is often called Cox and Redfern plot. We can calculate the activation energy for the LDPE catalytic cracking. See, this is the plot. You see that the blank sample without the addition of catalyst, the observed activation energy is 440. But when you use the zeolite, it decreased to 374. But this is purely microporous. But when we introduce the mesoporosity, the observed activation energy is further decreased, showing the enhancement of catalytic performance because of the introduction of mesoporosity with the preservation of microporosity. So it's interplay between microporosity and mesoporosity. And this is this work is is conducted by my students, my master students. We have published it RC Advances this year. And we also use the Aluminosilicate. This time we use the fly ash. So fly ash is actually a waste resulting from the combustion of coal, but it consists of high amount of aluminosilicate, either amorphous or crystalline. And we have to upgrade this for the use as absorbent for the removal of heavy metal cations. You'll see, this is fly ash, and we upgraded or we performed activations using the alkaline solution. There are at least four systems or four alkaline solution which we use to activate this fly ash. See, using potassium hydroxide, we call it as KGP. So GP is not Grandprix, but it is geopolymers. So KGP, sodium GP, and these two last sample we add some silicates. So you see, this is the XRD. The crystalline components are mullite, hematite, and quartz. Seems similar. It seems that nothing changed from the XRD pattern. But you see, the crystalline components, quartz, mullite, hematite. For example, quartz, it is dense silicate. It is dense silica, which should not have absorption capacity. So, what's part functioning as adsorbent? It should be the amorphous part, not the crystalline part. So what we do, we subtract this crystalline profile, and we perform the convolution only on the amorphous part. And you see, the width, the full width at half maximum of the treated samples, it is decreased. It is decreased, showing the more organized structure within the amorphous, not the crystalline. So you see from if we compare potassium and sodium, you'll see sodium will result in more organized structure. In the K seal and sodium seal also same trend. It is also confirmed by the aluminum mass NMR. You'll see the full width at half maximum disorder in mass NMR is the same as the order in XRD. So they are confirming each other. So there are structural alteration within these geopolymers. So this structural alteration is actually reflected in the textural properties. You'll see, this is the NLDFT pore size distribution of the samples. See, fly has very broad distribution, but when you have treated with alkaline solution, it shifts. It shifts to still broad but narrower compared to that of fly ash. And you see the intensity of sodium, is higher than that of potassium, as well as for the K seal and sodium seal samples. And also you see at the electron microscopy, this is fly ash, very it is big particles. But when you use sodium, the size is decreased, as well as potassium also. But you see, sodium decrease the size of fly ash to further extent than that of the potassium. So see, all of the characterization data are confirming each other. We have tested it in, we have studied, we have investigated the isotherm, the kinetics, as well as the thermodynamics, but I do not show here because of the time. But if you are interested, you can see our latest publication in Journal of Hazardous Material. This is performed by my PhD student, which have been graduated 2 months ago. So you see, if we plot the peak to FA, the peak to width, the full width at half maximum from the XRD data. See the full width at half maximum from the aluminium mass NMR spectra, as well as the BET surface area, with the maximum absorption capacity of the sample. See, well correlated. But when we try to correlate the maximum absorption capacity with the chemical composition, which is the silicon to aluminum ratio, it's random. We cannot find any correlation. But you see, it is often the lower the silicon to aluminum ratio, you know, the higher the negative charge, because the aluminum is more. There is more aluminum, which means there is more negative charge. So if there are more negative charge, it should attract the cations, but it's not. So rather the absorption capacity of copper 2+ is governed by the structural properties of the adsorbent, at least for our sample, at least for the geopolymers. So you see, this is we try to illustrate. So you see, natrium or sodium system will give more organized geopolymer compared to that of potassium. Still, still amorph, but at least more organized. So in summary, the catalytic performance of zeolite can be, enhanced by modification of its pore structure. It is by adding, by introducing a larger porosity. It can be mesoporosity 2 to 15 nanometers, or it can also be microporosity higher than 50 nanometers. And we can control the extent of desilication in SZ13, by using the presence of organics. And unlike the conventional desilication, this technique preserves the crystallinity of SZ13 as well as increase its catalytic activity, due to the presence of mesoporosity. And in the environmental application, fly ash, which is actually waste, can be upgraded. It can be activated as effective adsorbent for the removal of heavy metal cations, and the structural properties of the adsorbent strongly strongly governs its function as adsorbent. And I would like to thank respectively the Directorate General of Higher Education and Technology for our institute, ITB, for giving us the funding, as well as our newly established Research Center for Nanoscience and Nanotechnology, as well as the Asahi Glass Foundation for giving us give us partial funding, and as well as my ex-students who have now graduated for doing the experiment. Mrs. Mariani, Mr. Adroit, he's now in Kyoto University pursuing his PhD, and as well as Dr. Nita Dharmayanti, he's now a lecturer in Riau University. I thank you all for your kind attention.